Welcome to a course on complex analysis. In the previous lecture, we have seen the necessary condition for the differentiability of complex valued functions. We have also seen that the condition that we derived was not sufficient to ensure the differentiability. But so, in this lecture, we are about to see the sufficient condition for the differentiability of complex valued functions via CR equations. As said, we are now about to see the sufficient condition for differentiability. So, in the previous lecture, we have seen the necessary condition, that is, if the function satisfies if the function is differentiable, then it will satisfy Cauchy Riemann equations, right? And also, we have seen an example that tells you that a function which satisfies CR equation fails to be differentiable as well. So that was only the necessary condition, right? So the sufficient theorem is given as the sufficient condition is given as a theorem here. So that is, let the function f of z, that is u of xy plus iota times of v of xy, let this function be defined throughout some epsilon neighborhood, just a minute, yeah, throughout some epsilon neighborhood of a point z naught equals x naught plus iota times of y naught, and suppose that we are going to make some suppositions, that is the base assumptions. The first order partial derivatives of the functions u and v with respect to x and y exist everywhere in the neighborhood. The second supposition that we are about to make is those partial derivatives are continuous at point x naught y naught and satisfy CR, that is Cauchy Riemann equations, ux equals vy and uy equals minus vx at the point x naught y naught. Okay, these are the suppositions that we made. That is, here what we have assumed is that we have a function, okay, which is defined throughout some epsilon neighborhood of the point z naught. Here, why we are particularly choosing the point z naught? Z naught is some arbitrary point in the domain at which we are going to talk about the differentiability. Okay, if you have to talk about the differentiability throughout the domain, you can keep changing the point z naught. Okay, whatever may be the point that you choose, you will have to choose some epsilon neighborhood around it, and in the neighborhood we must have these conditions which are supposed, in the sense, if these conditions are satisfied, then we are going to get something. So what we are going to get, so that is what we are going to tell now. Then your f prime evaluated at z naught exists and its value being f prime evaluated at z naught is going to be ux plus iota times of vx, where the right hand side, that is your ux and vx, is to be evaluated at x naught comma y naught. Now you may ask me, why are we writing this in terms of x? Can't we write this in terms of y? Yes, of course we can write. So just because these are supposed, these CR equations is supposed, you may also write your f prime evaluated at c naught as ux. Instead of ux, you may replace vy. So vy plus iota times of, instead of vx we shall write minus uy. So this one, if you take minus iota outside, then you would have what? Uy, then plus iota times of vy. Okay, so this may be written this way as well. Okay, if you know the partial derivatives of u and v with respect to any of the variable, be it x or y, you can always write down the derivative of the given function evaluated at the point z naught whenever the values are known. Okay, this is the statement of the sufficient condition. Now we are about to prove this condition. Okay, so let us start the proof formally. Okay, if I were to change the color, yeah. Okay, so given the function f of z, that is uxy plus iota times of vxy, is defined, or we may say well defined, on some epsilon neighborhood of z naught. Okay, also the conditions a and b are supposed. So what were they? That is ux, vx, uy, vy exist and they are continuous as well. Okay, they must exist and they are continuous in whatsoever the epsilon neighborhood that we have chosen, in the epsilon neighborhood chosen. Okay, also ux equals vy and uy equals minus vx. It also satisfies the CR equation. So we have written the suppositions. Okay, now we are about to proceed with our proceedings. Okay, let us write delta z as delta x plus iota times of delta y. Okay, and here 0 is smaller than delta z, which is smaller than epsilon, because we are talking the things in the epsilon neighborhood. So that is why this condition is imposed. Then we shall write delta w as f of z naught plus del z minus f of z naught. Okay, and we also know this del w shall be written as del u plus iota times of del v. Okay, thus here what is happening? Your del u is nothing but u of x naught plus del x comma y naught plus del y minus u of x naught y naught. So this is the change in u, and the change in v shall be written as v of x naught plus del x, comma y naught plus del y minus v of x naught y naught. Okay, so these things are there. Now we shall do one more thing. That is, since the partial derivatives are continuous, that is, since your ux, or let me write this way, since partial derivatives of u1v are continuous at the point x naught y naught, we shall write delta u as ux x naught y naught delta x plus like uy x naught y naught delta y plus some epsilon 1 delta x plus epsilon 2 delta y, and similarly your delta v may be written as vx x naught y naught delta x plus vy x naught y naught delta y plus epsilon 3 delta x plus epsilon 4 delta y. Okay, so actually we are going to plug all these things somewhere. So let us mark this as equation 1 and these as equation 2 and 3. Okay, here whatever we have written is due to the fact that these are valid. Actually, these are valid. This is what we have learned in the functions of several variables. Okay, you can just refer the courses on functions of several variables to write these things. Okay, how these things came. Now, after here, actually here we need to say one more things, right? This epsilon 1, epsilon 2, epsilon 3, epsilon 4 tend to 0 as your delta x, delta y approaches to 0, 0 in delta z plane. Okay, therefore, now our delta w becomes what? Actually this is delta u plus iota times of delta v, right? So delta u is ux evaluated at x naught y naught delta x plus uy evaluated at x naught y naught delta y plus epsilon 1 delta x plus epsilon 2 delta y plus iota times of vx x naught y naught delta x plus vy x naught y naught delta y plus epsilon 3 delta x plus epsilon 4 delta y. Okay, here now using the fact that CR equation is valid, that is ux is equal to vy, and those things we shall write, right? So let me change the things only in the imaginary part. Let me write things as it is. Okay, let us try to have only the derivatives with respect to x. Okay, that would be better. So delta x, so this ux is equal to by and vx is equal to minus uy, so this may be written as minus vx evaluated at x naught y naught multiplied with delta y, this quantity as it is. Okay, and then we have epsilon 1 delta x plus epsilon 2 delta y plus iota times of, we shall have this as it is, delta x, and this one is with respect like ux is equal to vy, so we change this to ux delta y plus epsilon 3 delta x plus epsilon 4 delta y. Now combine the terms, that is, you shall write ux this quantity with delta x plus iota times of delta y. So actually what I am doing is that I have combined these two terms and wrote here. Next, I think if I write this in different color, you people can understand easily. So instead of writing this in black color, let me write this way. I'll make a tick mark in that color and I will write that quantity in the same color in which I have made the tick mark. Okay, so this is what I'm having. Next, this quantity and this quantity. Here, I would like to take. Okay, so first of all, let me initially write iota times of Vx x naught y naught. Here I don't have the iota term, right? So Vx x naught y naught iota times of delta x minus delta y. So this is what we have. Now, so combining these two terms, what I am going to get is that epsilon 1 plus epsilon 3 multiplied with delta x, and with these two terms I would have epsilon 2 plus epsilon 4 times of delta y. Okay, now we'll have to do few more things, that is, so this ux x naught y naught, and initially we have assumed that this is delta z plus vx x naught y naught, from which I would like to take iota outside. So when I take iota outside, this becomes delta x plus iota times of, sorry, I think I have taken only iota outside, right? Yeah, hope I am right. So minus 1 shall be written as iota squared. So this actually here, this minus 1 shall be written as actually only this quantity. Let me write it in different color. So this is iota delta x plus iota square delta y. So from which I have taken iota outside and I have the remaining terms here. Okay, plus epsilon 1 plus epsilon 3 delta x plus epsilon 2 plus epsilon 4 delta y. Okay, now this is simply ux x naught y naught delta z plus iota times of vx x naught y naught delta z plus epsilon 1 plus epsilon 3 delta x plus epsilon 2 plus epsilon 4 delta y. Okay, now this is what, this is del w. Let me write del w upon del z. This is ux x naught y naught. So del z gets cancelled, plus iota times of vx x naught y naught, again delta z gets cancelled, plus epsilon 1 plus epsilon 3 times of delta x upon delta z plus epsilon 2 plus epsilon 4 times of delta y upon delta z. Okay, let me mark this as equation, like, if I okay, let me mark this as equation 5. If we missed 4, this is your equation 4. Okay, now we will have to observe something. We know that your delta z is delta x plus iota times of delta y. Okay, and due to the fact that what, so if this is true, then your absolute of delta x is smaller than or equals absolute of delta z, and absolute of delta y is smaller than or equals absolute of delta z. Thus, absolute of delta x upon delta z is smaller than or equals 1, and absolute of delta y upon delta z is also smaller than or equals 1. Therefore, absolute of epsilon 1 plus epsilon 3 times of delta x delta z may be written as absolute of epsilon 1 plus iota times of, actually I have missed iota somewhere, right? So yeah, here we have iota, so here we would have plus iota times of epsilon 3, and here also the same, plus epsilon 2 plus iota times of epsilon 4 plus iota times of epsilon 3 plus iota times of epsilon 4. Exactly. So we missed it here. You can just go through the equation number 4 and see where I missed these things. While doing the calculation, be a little more careful, or if you find it at any point, you can just change it. Right? Yeah. So this is absolute of this quantity. So this is again smaller than or equals absolute of epsilon 1 plus absolute of epsilon 3. Okay, this is the entire absolute value, and these are some separate values. Actually, this is gonna happen, and actually here also we have the iota. So epsilon 2 plus iota times of epsilon 4 delta y upon delta z. Here also we are going to have the same thing. So epsilon 2 plus iota times of epsilon 4, which is smaller than or equals absolute of epsilon 2 plus absolute of epsilon 4. So these things we have. Okay, this means these quantities are very very small. Now we shall take limit your delta z approaches 0, that is your delta x comma delta y approaches to 0 0. Okay, to delta w upon delta z. So if you look at these things here, this quantity is smaller than absolute of, like, so this quantity goes to 0, and like, actually what I'm trying to say is, when you make your delta z goes to 0, what happens here is that this quantity goes to 0 and this quantity goes to 0 as your delta z approaches 0, using the fact that we shall write this quantity as ux x naught y naught plus iota times of vx x naught y naught. Okay, this is nothing but your d dw upon dz or your f, okay, evaluated at the point z naught, or simply f prime evaluated at z naught as ux evaluated at the point x naught y naught plus iota times of vx evaluated at the point x naught y naught, and actually this completes the proof of the sufficient condition, right? So now we are about to see a problem. Uh, so the first problem tells that is f of z is e power z. Okay, we know that derivative of e power z is e power z itself, but we are going to prove this. Okay, we write this as e power x plus iota times of y. So this is e power x multiplied with e power iota times of y, and this becomes e power x multiplied with cos x plus iota times of sin y. So this is e power x cos x plus iota times of e power x sin y. Therefore the function u is e power x cos x, and v of xy is e power x sin y. And you just try to find out these things. Your ux is what? U e power x cos x, the same. I think it's cos y. So yeah, I wrote it wrong. So e power x cos y, and your vx is also e power x sin y. So your f prime at z is ux plus iota times of vx. So e power x cos y plus iota times of e power x sin y. So e power x cos y plus iota times of sin y. So this shall be written as e power x e power iota y. That becomes e power x plus iota y, and that is simply e power z. So the derivative is the same function itself. Okay, this is true for all. That is your f prime of z is same as that of your f of z for all z in the set of complex numbers. Okay, we have proved it with the help of the thing that we have directly given in the uh, statement of the sufficient condition. Now let us do the other way. Okay, let me find uy. So when I try to find uy, I am going to get minus e power x sin y. Okay, and vy is e power x cos y. So we know f prime of z may be written as yeah, we shall refer our f prime of z is vy plus iota times of minus uy, right? Vy is e power x cos y minus iota times of uy, that is minus e power x sin y. So this becomes e power x cos y plus iota times of e power x sin y. Now you can take e power x as a common, and e power cos y plus iota times of sin y becomes e power iy, and that is e power x plus iota times of y, that is e power z. Okay, so whatever may be the way in which we are coming, we have obtained the same thing. Okay, so this validates your sufficient condition, right? Thank you.